So today we will be presenting a proof of the intermediate value theorem. I'm Emily.
I'm Toby.
Okay.
What is an epsilon delta proof? An epsilon delta proof proves or disproves the existence of a limit. It confines values functions at an arbitrarily small interval around an undefined point, and using epsilon and delta, epsilon compares closeness of a function's output to the limit, and delta compares the closeness of a function's input to the point where the limit is being taken. The intermediate value theorem states that if f of k is less than k is less than f of b, and a is less than c is less than b, and f of c equals k. As an example here, if a function is differentiable, then point C, which is between points A and B, will always be in the function, whereas if the function is not differentiable, then point C will not be in the function.
Okay, so we will be proving this. So if f of x is continuous on the interval a to b inclusive, and k is any value such that f of a is less than or equal to k, which is less than or equal to b, then there exists an a in the element of a comma b such that f of c equals k. So first we're going to define a set where x exists in a comma b, where f of x is less than k. We're going to let c be the supremum of the set. So we're going to define the set, and due to the continuity at a, we can keep f of x within the elements of greater than 0 and of f of a by keeping x sufficiently close to a. And since f of a is less than k, when the element is half the distance between k and f of a, no value sufficiently close to a can be greater than k. Therefore, there are values greater than a in the set. And for this reason, a cannot be the supremum. Some value to its right must be. And so this is pretty intuitive, because if it wasn't true, then it's just not the supremum by the definition. And then same thing, due to the continuity at b, we can keep f of x within greater than 0 for of f of b by keeping x sufficiently close to b. And since k is less than f of b, it is half the distance between k and f of b. So every value sufficiently close to b must be greater than k, therefore b cannot be the supremum of c.
When c is not equal to a and c is not equal to b, but the element of c, the interval a to b inclusive, it must be the case that c is in a comma b, f of c equals
So we're going to show that f of c equals k. So let us begin. Since f of x is assumed to be continuous on the interval a to b, and c is an element of a to b, we know that the limit of as x approaches c of f of x is equal to f of c. Thus, by the epsilon delta definition of a limit, for any element that is greater than 0, we can find a delta that is also greater than 0. So that whenever c minus delta is less than x is less than c plus delta, such that x is not equal to c, we must have f of c minus the element is less than f of x, which is less than f of c plus the element. So we're going to consider any value such that the element is greater than 0, and that the value of delta that goes with it. Now, there must exist some x naught that is in c minus delta comma c inclusive, where f of x naught is less than k. If there wasn't, then c would not have been the supremum of the set. Some values to the left would have. However, since c minus delta is less than x naught, which is less than c plus delta, we also know that f of c minus the element is less than f of x naught is also less than f of c plus the element. In the case not inferred by the continuation of f, this says that f of c minus the element is less than f of c is less than f of c plus the element. So when we focus on just the left side of the inequality, it yields f of c is less than f of x naught plus the element. And since we remember that f of x naught is less than k, we get f of c is less than k plus the element. However, there also must exist some x that is an element of C inclusive to C plus delta non-inclusive, where f of x1 is greater than or equal to k. If there wasn't, then C would not have been the supremum of the set. Some value to the right would have been. However, since C minus delta is less than x1 is less than C plus delta, we also know that f of C minus the element is less than f of x1 is less than f of C plus element. So when we focus on just the right side of the inequality, we get f of x1 is less than f of C plus the element. And if we subtract the element from both sides to obtain f of x1 minus the element is less than f of C. Remembering that we were given f of x1 is greater than or equal to k, it yields f minus the element is less than f of C. However, the only way this holds for any element greater than 0 is if f of C is equal to k. That's the end of the proof.